Hello everyone, this is my smart timer. And this is the free fall adapter. I've been doing some measurements, and the measurements with the large of these two balls are very interesting. This is in fractions of a second, 0.4180, and this here and this here, they're already violating Newton's theory, because these free fall times correspond to g values that are larger than the g value measured at sea level in Bremen, which are conducted in a vacuum. So here I don't have a vacuum, and I'm on a high mountain, like something like 3,000 meters above sea level. And so fix this real quick. And so it's quite strange to get g values that are higher than those at sea level. So here we press this button here, and then we release this. Okay, this is almost violating Newtonian physics. If it was 81, then it would be violating it. Well, here we pick the smallest number actually, because that's the most accurate one, because in this release mechanism there is a short delay. And I've got many such violations, Newtonian physics. What I was actually intending to do, what I'm still intending to do, is compare same mass, same size spheres, because they have the same air resistance, and so the drag coefficient is the same, because they're spherical, and yeah, the surface area and the mass which is pushing on the air. So this is not quite the same. This is 14 gram, and the other one is the iron ones. This one is 30 gram. This one I didn't weigh yet. I have to weigh it tomorrow. Yeah, so the hierarchy in the free fall times is right. It's the lead balls fall the slowest, which is what my theory predicts. Then aluminium is in the middle, which I didn't test myself, but it was tested in Bremen. And iron is the fastest. Now, I can't give very clear evidence on that from my own experiments. There are many other experiments though, and Cavendish experiments, but not so many free fall experiments. But what is very interesting is that iron in this mountain area here, in this Greek mountain village, is falling faster than aluminum in a vacuum in Bremen, which is near sea level. Like it's 14 meters above sea level, I think, Bremen, and this here is like 3,000. So that's quite interesting. And originally I wanted to use these this vending machine capsules for the free fall, but the problem is only magnetic things are recognized by this sensor. It's an electrical sensor, and so it works fine with lead and with iron, actually with steel. Actually, it works much better with lead. These are various lead balls, 3 gram to 14 gram. And I got some zinc here. I wanted to use it, but I can't use it because the sensor doesn't notice these plastic objects, and also it doesn't notice the marbles. So I will be ordering a laser gate, a photo gate, where during the fall, only at the very end, the laser is interrupted, and how long it's interrupted tells us the speed. So we're gonna be measuring the terminal velocity, and that also tells us the free fall acceleration. So this will be a better approach than this thing here, because this really works only for a couple of materials. Actually, it works much better for lead than for iron. Iron, sometimes the sensor doesn't pick it up, and then you get a strange value, like a ridiculously short time. And if you use something like this, which is not recognized at all, then basically it just counts the time from when you push this button until it dropped on that receiver platform. Yeah, so this thing here, this free fall adapter from Casco, it really only works with electrically conductive materials. By the way, this is my book. I use it here to fix this rod here. Well, it does just fine. It's not the best option, but it's fine. Yeah. Okay, that's all for today.